Hello and welcome. This will be a lecture on spatial econometrics. What we will do in this video clip is, first I will provide a few examples of the spatial econometrics models and the data that we use. Second, I will talk about the spatial weight matrix, which is a very important concept, and it could be based on contiguity or distance. Then I will talk about the spatial regression models, particularly the spatial lag and spatial error models. And finally, I will talk about the spatial dependence test, or so-called the Moran's eye. So let me start by providing a few examples. First one comes from real estate economics. So we all know that the house prices depend on the number of bedrooms, number of bathrooms, and so on. You can imagine a regression model on that. But they also depend on location. What the realtors are telling you is location, location, location. Which means that the prices of houses in the same neighborhood or that are close to each other or on the same block are similar. So this is an example of how spatial effects could be present. Another example is farmland values. So if we try to estimate a model where we have farmland prices in a certain county that could depend on the land rent that they could get on the government payments and so on, but they would also be similar if the counties that the farmland is located in are spatially close to each other, and then we will have to define spatially close. A third example comes from precision agriculture, where you can apply nitrogen to a field, and so yields for the corn that grows on that field would be different because you can apply different nitrogen in different areas of that field. But they will also be similar if the fields or the plots are spatially close to each other because they would have similar characteristics. So basically, this is an example of where physical distances or proximity of these objects or places is very important. Spatial econometrics could also be applied in economic sense. For example, if you have farms in different countries or something like that, proximity may not be defined necessarily on distance, but for example, it could be defined based on how many interactions you have between different sub-firms or different locations of the same firm, different offices of the same firm. Okay. So spatial econometrics basically would account for the presence of these spatial effects in regression analysis. So it will be more complicated than the linear regression model because we have to explore these distances from each other and so on, and we have to define who is a neighbor of who and how much different objects influence each other. Spatial econometric models are used in regional science, in urban and real estate economics, and economic geography. So there are a lot of applications for that. So notice the first bullet point that I have here. Spatial econometrics is a special type of econometrics. Note these two words. Spatial comes from space, spatial, and special is like a unique type of econometrics. So don't confuse the word spatial with special. That's how it's spelled. One of the unique things about spatial data is that it needs to be geocoded for location, which means that basically every single observation in your data would need to have either coordinates, borders, distance, or some other geodata in order for you to be able to do spatial econometric models. So data is much harder to find than, say, for some of the other typical models that we will consider in this class. Next, the spatial matrix that we will talk about later, it defines the neighbors, which observations are spatially close and what are their effects, how much they influence each other. Because if two houses are very close to each other, they would influence each other a lot more than, say, if two houses are a few streets away from each other, then the effect would be smaller. And we would need to account for the spatial dependence in a regression model. So this was what we're going to be doing. So next, take a look at this graph that I have here. And this is about this is the state of Kentucky in the U.S. And we have counties in this state. And what's plotted on there is the poverty rates in these counties. And if you have them darker, this means higher poverty rates. So you can see here the region of the Appalachian Mountains have much darker counties, which means higher poverty rates. So do you think that this graph has spatial dependence effects, or it doesn't? That's right, it has them, because you can see some clustering. You see, like, the darks tend to be together, these tend to be together, these tend to be together, and so on. So if they were like completely random and you couldn't see any pattern, that would mean there's no spatial effects. So how does that help us that there are spatial effects? Well, it helps us in certain way. Like, for example, suppose that you don't know the value of, say, this county. What is the poverty rate in this county? What can you do? Well, you can look at the ones around it, and you can maybe take the average or something like that, and you will be exactly right. Now, if you look at this one and you take the average of those, you won't be exactly right, but you would be close. Or this one, you will be close, and so on. So this is what spatial econometrics does. It not only considers the characteristics of an individual county, but how do the neighbors influence the value here? And who are the neighbors? Are these just the neighbors, or are these neighbors? Is it a larger radius? So you, as a researcher, would need to decide these things. Okay, so next let's talk about spatial weight matrix. So we would have a matrix of weights, and these weights would provide the structure of the spatial relationship among the observations. So the matrix would provide information about which of the observations are considered neighbors and how their values are related to each other. We will define the spatial weight matrix as W, and the elements would be small w, I, j, would indicate whether observation I and j are spatially close. Another thing that we will talk about is that spatial weight matrices would need to be row standardized, which means that the weights would need to sum up to 1 on each row. We will see this later on why. And we will consider two types of spatial weight matrices based on contiguity and distance. So let's start with the first one based on contiguity. Contiguity basically means if they touch. So think about counties or something like that. If they touch, if the observations are contiguous, which means next to each other, they could share a border. Like, so imagine counties, you could share a whole line, or a vertex, you could just share the dot, the point at the end that could touch to each other in terms of counties. But that's how we would define whether or not they're close to each other. And we could use GIS ArcView or some other software that could recognize spatial weights if you just give them who is a neighbor of who. But in general, most statistical software cannot recognize contiguity. You have to have done this in a specialized software that would have spatial capabilities and then use these data into your software program. Okay, so the spatial weight matrix W would have the elements as defined as follows. Wij would be equal to 1 if I is contiguous to j and 0 otherwise. So if units I and j are neighbors, the spatial weight would be equal to 1 and otherwise 0. So let's consider an example here. the spatial weight matrix based on contiguity would have, and I'm coming up with this like I'm making it up. So suppose that units 2 and 3 are neighbors and units 3 and 4 are neighbors. But those units 2 and 4 are not neighbors, and 1 is not a neighbor of anyone. So how would this spatial weight matrix look like? Okay, so if units 2 and 3 are neighbors, we would have row 2, column 3, that would be equal to 1, and then row 3, column 2 equal to 1, because 2 is a neighbor of 3 and 3 is a neighbor of 2. So now we also have that units 3 and 4 are neighbors, therefore this would be equal to 1, and units 4 and 3 are neighbors, therefore this would be equal to 1. So all the neighbors get a value of 1, and all that are not neighbors get a value of 0. So notice another interesting thing about these spatial weight matrices is the diagonal element are equal to 0. So these are you a neighbor of yourself? So is unit 1 a neighbor of itself? The answer is no, and we would put that as a 0. This is just a convention. So we would have these equal to 1. So now notice that these rows would sum up to anything. Like here we would have 1, here we would have 2, and here we would have 1. So one thing that we can do is we can row standardize by dividing each entry by the total for that row. So for example, the total for that row here was 1 from above, so there's not much to do. But the total for this row is 2. Therefore, we would divide that 1 by 2, which would get 0.5, and we would divide this 1 by 2, which would get us 0.5. The total for this row is 1 for row number 4, and therefore we just divide the 1 by 1, which is a 1. So now, what we've done with this matrix is row standardized, so that each of the rows now sums up to 1. Why is that important? Because now each row would represent the value for that unit as a weighted average of its neighbors. So for example, look at this guy. This is unit number 4, or observation number 4. It has two neighbors, observation number 2 and observation number 4, and they equally influence this. Therefore, if we don't know the value for the third observation, what we can do is take the value for the second one and the third one, put these as weights of 0.5, and we would get the value for y3. And this is what we are doing here. y3 equals 0.5 of y2 plus 0.5 of y4. We're reading off this row. So in general, we would have yi equals summation over j of wij times yj. So yj's are the values for the neighbors, and these are what's the influence of those neighbors. So for example, if you look at observation number 4, that one had only one neighbor of neighbor 3, and so the value would be y4 would be equal to y3. That's the only thing that we have information of. So again, this row standardization is important because if we have a weighted average formula, the weights would need to sum up to 1. And we can predict the values for each observation based on the values of the neighbors. Okay, so we talked about the spatial weight matrix based on contiguity or proximity of each other. Now we will talk about the same spatial weight matrix if it's based on distance between the observations. So the first thing to talk about is coordinates. We need to know the coordinates or the locations of these observations. Typically the x-coordinate and the y-coordinate, or the longitude and the latitude for each of these observations, in order to calculate the distance between the observations. One thing that is typically done here is that with county level data, we can use the distance between the centroids or the center points of the counties. So imagine like a county is like a blurb like that, and if you have about the center in the middle, then when we calculate distances from that middle to from this centroid to the centroids of other counties. And so if two counties are close to each other, their distance would be a lot smaller than two counties in the opposite side of the state. So different software packages can typically calculate these spatial weight matrices if the x and y coordinates are provided for each observation. So let's call dij would be the distance between observations I and j, and we would assume that there are no spatial effects beyond a certain distance band, d, capital D. So imagine, like, for example, if we have a big state and we would say, okay, well, land values depend on each other, you know, if these counties are close, but say anything over 200 miles becomes irrelevant. Basically, it's not going to affect each other. And so if we put this distance band equal to 200 miles, then anything above that would no longer be neighbors and would no longer affect each other. Okay, so here is another example of the spatial weight matrix. This one can be constructed based on distance, where the units are within a specified radius. They would have a weight of 1, their neighbors otherwise 0. So wij would be equal to 1 if the distance between I and j is less than d, the distance band, and 0 otherwise. So say in my example, anything below 200 miles would have a value of 1 if these counties are close than 200 miles from each other, and otherwise would be 0. And the spatial weight matrix would look similar to the one in the previous section, but it will be based on distance or and not contiguity. Now we have an alternative specification where the spatial weight matrix can be constructed based on distance, where this distance dij would receive a weight that's inversely proportional to the distance between the units, and 0 if they're beyond a certain distance span. So here we have wij, the elements would be equal to 1 divided by dij. So basically, if the distance is less than the distance band, they would be inversely proportional to how far they are away from each other. So the farther they are away from each other, the smaller the influence would be on each other, and 0 otherwise. So let's go ahead with an example. Suppose that we have a spatial weight matrix based on distance, and I'm making these numbers up, where units 1 and 2 are neighbors with the distance equal to 5, and units 2 and 3 are neighbors with distance equal to 2. How would that spatial weight matrix look like? And here we have it. Distance, so units 1 and 2 are neighbors, and the distance is 5, therefore the value is 1 divided by 5, which is 0.2. And same thing, unit 2 and 1 are neighbors with distance 5, therefore this is a 0.2. And then we have unit 2 and 3 are neighbors, and 3 and 2 are neighbors. So these two values would be equal to 1 divided by the distance of 2, or would be equal to 0.5. Okay, so this is how the spatial weight matrix looks like. And now we need to row standardize it by dividing each entry by the sum for the row. So here the sum for the first row is 0.2. So if we divide 0.2 by 0.2, this is how we get this value of 1. Here the sum would be 0.2 and 0.5 would be 0.7. So if we divide the 0.2 by 0.7, we would get 0.3. And if we divide 0.5 by 0.7, this would be a value of 0.7. Next, the sum here is 0.5, therefore dividing it, that would be equal to 1, and here there's nothing to do with this row. So this would be a row standardized matrix. And now you can say, if we don't have the value for the first observation, we would just pick the value for the second observation. And if we don't have the value for the second observation, we would pick 0.3 times the value for the first one plus 0.7 times the value for the third one, and that would be the best approximation that we can do. Okay, so here's my little assignment to you now. create a spatial map for the unit locations, which means I talked about now unit 1 and 2 being neighbors with distance 5, 2 and 3 being neighbors. So how are they located in space? So 1 and 2 would have a distance of 5, and 3 and 4 would be equal to 2. And if you also want to make it more complicated, figure out where these neighbors would be. The 2 and 3 would be neighbors, and 3 and 4 would be neighbors. So which ones would touch with which ones? These are not based on distance. Okay, so let's see who's going to create the map of how these counties are located. This is an interesting assignment. So, people ask me, how do you know which matrix to use, the one based on contiguity or distance? And it's up to you. Both methods are used in the literature. So you will need to think about which of the two methods better serves your problem. So for farmland values, for example, the neighbors would be based on distance would be more appropriate, because it doesn't quite matter if the counties touch each other, if they're big or small, you know, that the whether or not they're next to each other doesn't matter as much as how far they are from each other. But for residential values, maybe it would be more important that they're based on contiguity or the neighborhood blocks or something like that, rather than distance necessarily. You know, if they're in the city. So you're the one who decides that. So to summarize here, here are the properties for the spatial weight matrix. First of all, the diagonal elements are set to 0, because the notation is that you're not a neighbor of yourself. And the non-diagonal elements are non-zeros for observations that are spatially close, and 0 for those that are far away. So if you're a neighbor, you have a positive value. If you're not a neighbor, you have a 0. As you have this distance band going to 0, the spatial regression model would approximate the results of OLS. Why? Because we will have no spatial effects. So yeah, so if you have no one affecting anyone else, that would be a general OLS model. Next, the spatial weight matrices are row standardized, which means that the row elements would sum up to 1. And this is because you can create weighted averages for the values. Next, the dimensions of the spatial weight matrix would be n times n based on the sample size n. So if you have anywhere like 50, 100, 2, 3, 400 observations, you're okay. But if you have too many of these, like imagine how many counties are in the US, they're over 3,000. If you're starting to create a matrix of 3,000 times 3,000, that will be almost very hard for software to handle. So I would say anything above maybe 500 by 500, not to attempt to do problems that would have such a big spatial weight matrix. Or if you have such a big matrix, make sure that at least not everyone is a neighbor of everyone. Like the neighbors are only a few in this spatial weight matrix. Next point that I have here is that it's typically the researcher that picks the distance band. And if you set your distance band to the maximum distance, then all the units would have at least one neighbor, if that's desirable for your problem. Next, I will talk about the two spatial regression models. These are regressions that would account for the spatial dependence of the data. And the spatial dependence can be added to a regression in two ways, using spatial lag and spatial error models. So first I will talk about the spatial lag regression. That one would be appropriate when the focus is on the spatial interactions of the dependent variable. And it's typically used when we know the structure of the spatial relationship. So for example, we would have the price of the house will depend on the prices of the neighboring houses. We know this is true for a fact. And in this case, the dependent variable y is the one that would have the spatial structure. So the spatial lag model would be a spatial autoregressive model that would include a spatially lagged dependent variable. And the spatial lag of a variable y would be wy. So remember this, W was the spatial weight matrix that we talked before. So how would the values for each of the observations be affected depending on who is the neighbor and what the influence is? So the dependent variable would be the weighted average of its neighbor's values. And here's how the model would look like. If we have a typical OLS model, we would have y equals x beta plus e, right? So one thing that we have here in addition to that is rho times w times y. So this is y is the same values as here. W is a spatial weight matrix. And here rho would be the spatial dependent parameter, which we will also estimate. So if we put this term on this side of the equation, this will be the reduced form equation. We would have I, the identity matrix, minus rho w times y equals x beta plus e. So in this case, the independent variables would be explaining the variation in the dependent variable that is not explained by the neighbor's values. Therefore, whatever we can explain in that dependent variable by the neighbors, we take it out. And then all the independent variables would explain only the remaining variation that we have. Okay, so contrasting would be the spatial error regression, and this model would be appropriate when we're interested in correcting for the spatial autocorrelation due to the use of spatial data. But that would be regardless of whether the model would be spatial or not. So in this case, we will not know exactly what the structure of the spatial relationship is. So we would include the spatial correlated errors due to unobservable features or omitted variables. So we could have, as an example, farmers' technology adoption decisions may be influenced by the neighbors. So suppose a farmer buys a tractor and the rest of the farmers like it, and therefore they start buying tractors and things like that. But you can't say that that depends on distance or proximity or anything like that. It will be more complicated than that. So in this case, we may be using the spatial error model rather than the spatial lag model that we talked about before. So here the error term E would have the spatial structure. So the regression model would be the simple OLS regression model, but this error term E would be, this spatial error term E would be the one having the dependence, and that would be lambda WE plus U. So this W would be the spatial weight matrix. So if we substitute this back into the equation here, and then simplify the equation, we would have what I will show you on the next page. But first of all, put this term on this side, and you would have the identity matrix minus lambda W E equals U, and you could put this term on the other side with a minus to the power of minus 1. Plug it in back into this equation, and this is what you get. So here the spatial regression model would be of this form, where both the dependent variable and the independent variables are multiplied by these terms, the spatial dependence terms. And here the spatial dependent parameter lambda would also be estimated. So in this case, we would be explaining everything, the dependent variable, like we would be explaining the variation that's left over after we remove the effects due to the neighbors, and also the independent variables would be plugged into the equation after we remove all the variation due to the neighbors. And so we just have the pure effects after we account for these spatial effects. Okay, so the last thing to talk about is the spatial dependence test, and we would like to know whether or not there is any spatial dependence, and this will be the Moran's I test statistic. So here is this I test statistic would be equal to n divided by s subscript O, and we would have E prime WE divided by E prime E. So S0, this term here, would be a standardization factor that corresponds to the sum of the weights for the non-zero cross products. So here we would have the summation over I and j of all these spatial weights. Okay, so if we have row standardized weights, we would have S0 would be equal to n, because we already know that all the rows sum up to 1, right? Remember this from before. Well, if all the rows sum up to 1, we would have all the columns now sum up to n, because that's the dimension of this matrix. So we would have this would be equal to E prime WE divided by E prime E. And so this test statistic here would depend on how much this matrix here affects the results. Would it make this close to 0, or would it make this close to 1? And that's how we would decide whether or not there's any spatial dependence. If this is close to 0, then there's no dependence. If this is closer to 1, there would be a spatial dependence. So again, we talked today about spatial error models and spatial lag models,